This is lesson 2-7, probability of compound events. In the last lesson, we did just general probability. We learned the difference between probability and odds, and we learned how to deal with just the probability of one event. Today we're going to talk about probability of multiple events, what we call compound events. An independent event is an event that does not influence another event. For example, rolling the dice. If I roll the dice, no matter what I get the first time, it has nothing to do with what I might get the second time. Just because I rolled the 6 this first time doesn't mean I can't roll the 6 the next time, because the 6 doesn't get taken off of the number cube. It stays on there, so therefore it's independent. It has nothing to do with the first roll, has nothing to do with what I'll get on the second roll. A dependent event is an event that influences each other. The occurrence of one event affects the probability of the second event. For example, let's say I have these following cards on the table here. A 2 of clubs, a 2 of hearts, a 2 of diamonds, and a 3 of clubs. If I was to take one of these cards away and not replace it, the probability of pulling a 2 the second time will be affected by the fact that the 2 is not back in the deck. If I said, what is the probability of pulling a 2? Well, there are 3 2s out of 4 cards, so the probability would be 3 out of 4. Well, if I ask, what is the probability of pulling a 2 and then pulling another 2, if I pull a 2 the first time, my probability goes down the second time. Instead of being 2 out of 4, it is now 2 out of 3, or 3 out of 4, and then 2 out of 3. So this is what we call a dependent event. If I don't replace the card without replacement, the second probability depends upon what I pulled the first time. Therefore, it's called dependent events. If I do replace the card, it continues to be an independent event. So I'm going to do probability of compound events. There are 2 rules for probability of compound events. Probability of 2 independent events. One event that does not affect another event. If A and B are independent, then the probability of A and B is going to be the probability of A times the probability of B. For example, if I was going to have cards, a number cube, the probability of rolling a 6 and then a 3 is the probability of rolling a 6 multiplied by the probability of rolling a 3, which in this case, rolling a 6 is 1 out of 6 times, rolling a 3 is 1 out of 6 times. So the probability of both of those events is 1 out of 36 times. I should be able to roll a 6 and then a 3 1 out of 36 times. The probability of 2 dependent events, if A and B are dependent, then it's the probability of A, then B. The important thing is you have to understand that if it's a probability of dependent events, you have to assume that the first event you want, you actually get. So if we do something that's not with a number cube, like say probability of pulling out if I have cards numbered 1 through 10, okay, 1 through 10 on my cards, and I don't replace them, what's the probability of pulling out a 5 and then a 2? Okay? The probability of pulling out a 5 out of the cards is 1 out of 10. There's 1 5 in all of the cards numbered from 1 to 10. Now that I pulled out the 5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The probability of pulling out a 5 and then drawing out a 2, you have to assume that you got the 5 the first time, so it's no longer in the deck. We didn't replace it. It's no longer in the deck. So the probability of the 5 is 1 out of 10 cards. The probability of the 2 is now 1 out of 9 cards, because there's 1, 2 left, but there are still 9 cards left in the deck. Not 10 anymore because the 5 is gone. So this probability is 1 out of 90. That's the difference between probability of independent events and probability of dependent events. Let's look at a couple of examples. Suppose you roll 2 number cubes. What is the probability that you will roll an odd number on one cube and a multiple of 3 on another cube? The first thing you have to determine is, are these dependent or independent? Does one event affect the other? It doesn't matter what I roll on the first cube, that will have nothing to do with the second cube, so these are what we call independent events. So we simply need the probability of an odd, and then multiplied by the probability of a multiple of 3. So we look at it. The probability of rolling an odd is 1 out of 2, because there are 3 odd numbers, and there are 3 even numbers, so 3 out of 6 reduces to 1 out of 2. The probability of rolling a multiple of 3, remember if we have 1, 2, 3, 4, 5, and 6, these are our numbers on our number cube. This is a multiple of 3, and this is a multiple of 3. Those are the only 2 multiples of 3, 3 and 6. So that would be 2 out of 6, which is 1 out of 3. So then those 2 probabilities multiplied together, 1/2 times 1/3 gives us 1/6. So that is the probability of rolling an odd and then rolling a multiple of 3. Let's say we have coins in our pocket. Suppose you have 3 quarters and 5 dimes in your pocket. You take out 1 coin and then put it back. Then you take out a second coin. Obviously, we're not looking. What is the probability that you take out a dime and then a quarter? Since we will put it back, right here, this phrase, put it back, these are independent events because no matter what I pull out the second time, it doesn't matter because I put it back in my pocket and I can pull it out again the second time. So whatever I pulled out the first time does not influence the second pull. So these are independent events again. So this would simply be the probability of pulling out a dime and then a quarter. So I need the probability of a dime times the probability of a quarter. Okay? So there are 8 coins total, 8 total coins. So the probability of pulling out a dime, there are 5 dimes, so 5 out of 8. The probability of pulling out a quarter, there are 3 quarters, would be 3 out of 8. And we simply multiply straight across the top, straight across the bottom. The probability of a dime times the probability of a quarter is 15/64. And we cannot reduce that, so that is the final answer for this particular problem. So that's the probability of a dime and then the probability of a quarter. This last problem. Suppose you have 3 quarters and 5 dimes in your pocket. You take 1 coin from your pocket, but we don't replace it this time. Key word here is, or key phrase, without replacing the coin. So we have not replaced the coin. What is the probability of taking out a dime and then a quarter? Now this becomes dependent because the second draw out of the pocket depends on what we drew the first time. So this is a dependent event. So we have a dependent event here. So this is going to be the probability of dime, then quarter. So we need the probability of a dime, and then we need the probability of a quarter after dime. Okay, so this is going to equal the probability of a dime times the probability of quarter after dime. So the probability of a dime, there are still 8 coins, 5 of them are still dimes, so this is still 5/8. Now the probability of a quarter after a dime, there are 3 quarters because we pulled out a dime. We have to assume that we pulled out what we were looking for the first time, which was a dime. So we pulled out a dime, so there are still 3 quarters left, but instead of 8 coins now, there are only 7 coins because I pulled that dime out of my pocket and I did not put it back. So this would be 3 out of 7. Multiply this, 5 times 3 is 15. 8 times 7 is 56. So the probability of a dime and then a quarter is 15/56. Now, this can work with word problems that are a little bit different. Let's suppose a teacher must select 2 students for a conference. The teacher randomly picks names from among 3 freshmen, 2 sophomores, 4 juniors, and 4 seniors. What is the probability that a junior and then a senior are chosen? Okay, a junior and then a senior. This is dependent because once you choose that person, you cannot choose that person again. A person can't be represented twice. I can't split my personality and become 2 different people. Well, maybe I could, but that's probably not a good thing. So we're looking for the probability of a junior. Ooh, I can't spell. A junior and then a senior. So that's the probability of a junior multiplied by the probability of a senior after a junior. So the probability of a junior, well, how many students do we have? We have 3 freshmen, 2 sophomores, and 4 juniors and 4 seniors. 4, 8, 10, 13. So we have 13 total students. That's good to know. Make sure you add those up right. So the juniors, there are 4 juniors out of 13 people, so 4 13ths. Now we picked a junior, So that person is out of the equation, so now we no longer have 13 people to choose from. We only have 12 people to choose from because we already picked that junior. Now we're looking for the senior after the junior. And there are 4 seniors, so that would be 4 twelfths. And of course, we can do a little bit of reducing here. 4 goes into 12 3 times, because that makes it a little bit easier to multiply. So then when we multiply straight across the top, we get 4, and straight across the bottom, we get 39. So 4 39ths is the probability of choosing a senior and then a junior. Last part of this problem, what is the probability that the teacher chooses a sophomore and then a junior? Same scenario. If I choose a sophomore, that person is out of the mix, so this is dependent. So we're looking for the probability of a sophomore, then a junior, which means the probability of a sophomore times the probability of a junior after sophomore. So the probability of a sophomore, there are 2 sophomores out of 13 people, so 2 13ths. That sophomore is now out of the equation, so we no longer have 13 people, we now have 12 people to choose from. And out of those 12 people, 4 of them are juniors. So we have 4 twelfths. Again, we can reduce. I can cross cancel. I can decide that 2 goes into self once and it goes into 12 6 times. And then I can reduce again and I can say 2 goes into 4 twice and 2 goes into 6 3 times. That makes this even easier. So then when we multiply straight across the top, we get 2 times 1, which is 2. Multiply across the bottom, 13 times 3, which is 39. So the probability is 2 39ths. Really, probability of compound events is not difficult. You just have to figure out whether or not the events are independent or dependent. If you pull the one person out, does it affect the next thing? If it does, it's dependent. If it doesn't, it's independent.